Okay, I think we can start the second talk this afternoon. It's a pleasure to introduce Miguel Moreno, who will talk about order trees and the category stability of super stable theories. Thank you very much.
Okay, so thank you very much for letting me talk in the conference. So I'm going to talk about Borel reducibility and super stable theories and ordered trees. So let's start by some motivation. So let's define IT of alpha, the number of non-isomorphic models of a theory T with cardinality alpha. So the spectrum problem talks about how these functions behave, and Shella answered how it behaves, giving us the main gap theorem, telling us that either you have the most amount of models, that is 2 to the alpha, or for every alpha, IT of alpha is bounded by this omega alpha. So he basically divided the countable complete theories in two types, classifiables and non-classifiables, the big amount of models and few amount of models. So we can understand that theorem as if T is classifiable and T dash is not classifiable, then T is less complex than T dash. And their complexity are not close. So this is a way to understand the complexity of theories, but there's another way using Borel reducibility. And the question is, did those two notions coincide?
It's inequality means that you could have less models than other alpha. Finally, alpha is 2. That omega 1, 2 is 2 to the other.
Oh, yeah, I think it is plus omega. It's plus omega. Oh, okay. Yeah, maybe there's a typo. Maybe there's a typo. I don't remember precisely. Okay. 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 So let's go to the generalized descriptive set part. So let's start by taking kappa and countable cardinal. So that kappa to the root kappa is equals to kappa. And now we take the generalized contour space, that is the set 2 to the kappa with the topology, with the bounded topology. That means that we take an element set of 2 to the root kappa, and we take the basic open set, that is the etas in 2 to the kappa, that extends set, that give us the basic open set. So now we have open sets, Borel, sigma 1, everything, so we can talk about continuous functions and so on. Now we code structure. So to code structure, we fix a countable relational language L, a bijection pi between topos kappa and kappa. And then we take that for every element in the contour space, we define the structure AF that will have domain kappa, and for every tuple A1 to AN, we say that this tuple is in the relation PM in AF, in the interpretation of AF, if and only if f of pi m A1 to AN is bigger than 0, so it's just a coding, it's quite standard. But now that we have structure, we can talk about models, that model theory. Of that model sum theory. So we take that T is a first order complete countable theory in a countable vocabulary, and we say that F and G in the contour space, they are equivalent in the isomorphism relation if the structures AF and AG model T and are isomorphic, or none of them models T. So by studying the isomorphism relation of a theory, we can study the complexity of the theory, but for that we will need reductions. So let's take E1 and E2 to equivalence relations in the contour space. Okay, and now we say that E1 is Borel reducible to E2 if there's a Borel function from the contour space to the contour space that satisfies that X is related to Y if and only if the images are related in E2. And then we write with this arrow, and I want to make a parenthesis, usually before put the smaller equals to B, but since in proofs I usually also use those symbols for another relations, so it becomes very heavy to read. That's why I used to use this arrow, but it's just for not making it so heavy to read. Anyway, so we can define the partial ordering sets of all first order complete theories, just saying that T is at most as complex as T dash, if and only if the isomorphism relation of T is Borel reducible to the isomorphism relationship of T dash. So now the question is if these two coincide. So is there a Borel reducibility counterpart of the main gap theorem in generalized descriptive set theory? And this is a very important question in the field, and it was the motivation for Friedman, Hütting, and Kulikov to write this book about generalized descriptive set theory. And so let's see what has been done so far with this question. So the first thing is to say what it's a non-classifiable theory. So these are the 4 cases. A theory is non-classifiable if it's unstable, stable and superstable with dot, or superstable with bottom. We're only talking about countable complete theories. So now, the first result that I want to mention is due to Mangraviti and Motor-Ross. They proved under these cardinality assumptions that if T is classifiable and shallow and T dash is not, then T is as much accomplished as T dash. So this talks about the first line that is just in classifiable theory. You have shallow, then non-shallow, and then you have the other ones, which obviously support that the main gap will be there. The second one is due to Friedman, Hütting, and Kulikov. They say that if T is classifiable and T dash is unsuperstable, then T dash cannot be less complex than T. So this also supports the idea that there should be a main gap in general descriptive set theory. Now, another one with Hütting and Kulikov is again under some cardinality assumptions. There is a kappa closed kappa plus CC forcing that forces that if T is classifiable and T dash is not, then we have that T is less complex than T dash.
Can you force the converse?
The converse? What do you mean by the converse?
I mean, this could be an indication of good measure of complexity. You can show that you can force this, but you cannot force the other.
Oh, that's open. You mean that you cannot, that classifiable theories are equally complex as non-classifiable ones?
So here you say it's consistent that the order and the Borel reducibility is what should be in model theory.
Yes.
But can you get the consistency of the other? Because if you can get both, then you don't have an indication.
Yeah.
You just can get this one, even if it's not true always. It's possible to get the right answer, but it's not possible to get the wrong answer.
Actually, you cannot because of the previous result of Friedman Hütting. So you cannot, but still, maybe for the others, this is only for sponsor perspective. So maybe the others you can force the others.
I'm sorry,
This in CFC, Mr. Okay, yeah, this is in CFC. What? Nope. Nope. No, this is general. Yeah, that one is a general assumption, but not the assumption that is a successor or something like that.
I'm asking about Moreno.
Okay. So, and there's another one that you can, it's again some cardinal assumptions. Again, it's some nice forcing, and then you can take any theory that is not classifiable, and you can force it to be the most complex theory, let's say, so that the others are lower. But each theory, you force there's some problem with the cofinality. For someone, you have to force something with omega cofinality, and with others with lambda cofinality. Okay, but these are forcing results. These are consistency results. So we are most interested in CFC, and then we have one result in CFC so far. That is that under again these usual assumptions. If T is classifiable and T dash is stable and superstable, then T is less complex than T dash. This is the utility and Kulikov. But this is about stable and superstable. So now we want to know what happens with unsuperstable theories, unstable theories. So let's talk about a bit about this result. For this result, we use this relation, this auxiliary relation. So the equivalent modulo omega cofinality. So this one is a relation in the Cantor space. So let's say S is the ordinals of cofinality omega. We say that eta and C are equivalent modulo omega cofinal if this set in which they are different intersected with S is non-stationary. You can think about it instead of thinking about this set, just think about that ordinals in which eta and c coincide is unbounded and closed under omega limits. It's equivalent. Okay. And this relation is important because we have this nice result that says that if T is countable complete classifiable theory over countable vocabulary, and again these cardinal assumptions, then the isomorphism relation of T is very reducible to the equivalence modulo omega cofinality. So the way to prove that, the way that was proved, that is the other, here is missing just the other part. But what Friedman proved was that equivalence modulo cofinality omega is very reducible to the isomorphism relation of stable and superstable theories. So now the idea is to modify that proof to obtain it for unstable theories. So it's going to be for unsuperstable theories. So that's what we're going to do. But first, we need to talk about how you construct these models. So to construct a stable unsuperstable theory, they work with colored trees. So a colored tree is a pair T and C. T is a kappa plus omega plus 2, 3, and C is a map. It's just a coloring map. It goes from the leaves to beta, some color. That's a colored tree. And Hittin and Kulikov, they proved that for every F in the Cantor space, you can construct a colored tree JF with two colors, so that for every F and G are equivalent modulo omega cofinality, if and only if the two colored trees are isomorphic.
So the tree has high omega plus 2.
Yes. Every branch is yeah. So, and from there they use some model theory construction from colored trees to construct the stable and superstable theories. So what you do now is start from this result, from the colored trees, and try to construct the unstable models of unstable theories. But to construct models of unstable theories, you know. Yes. Kappa plus means that every element has at most kappa successors. Kappa children. Omega plus 2, yes. Okay. So, but to construct models of unstable theories, you use another kind of trees, and those are ordered trees. So an ordered tree is, okay, is this tuple A predecessor symbol of level and smaller and order. So first there is a linear order I, such that A is a subset of sequences of I. A is a tree with unique limits. Also, you have the length of the elements of A, and Pn is just the level. It's a relation that tells you the level. So are just those etas in A such that has length n. That's Pn. Okay, but this is just a normal tree. Now the part of the order is the following. So you have that when you go and see every element of A and their successors, you see that here what we're telling is if two elements are comparable by the order, that means that they are successors of the same element. So the order is only for the successors of A, or successors of eta in A for every eta. So it's not ordering everything, it's just successors for every eta. This is what we're saying here. And the last condition is that this order is induced by the order I. So you're just ordering the children of each element and just ordering by I. So if you take the successor, for example, eta extended by x and eta extended by y, if eta extended by x is smaller than eta extended by y, that happens because x is smaller than y in I. So that is an ordered tree. So now we have two kinds of trees, colored trees and ordered trees. And we need both parts. One to deal with the omega cofinality equivalent relation, and the other to construct the models. So the question is how to mix them, and the solution is you order a colored tree. And to order a colored tree, we come up with the notion of kappa colorable linear order. So we say that a linear order of size kappa is kappa colorable if there is a function I and a function f from I into kappa, such that for every small set B and every element in I not in B, we say that we take every color and then there are kappa many copies of A respective to that type in the order. So basically, take an element A, take a small set, and then you say that for every color alpha, there are kappa copies of this element that satisfies the same type and have the color alpha. That's what we're saying. So this is a notion of saturation. That's what we want. Because if you have saturation, then you can order always the tree. But the problem is that if you take the saturated model of these linear orders, then you have category T. And we don't like category T because we want many models. So we want to approach as much as we can to saturation without reaching the saturated model. Okay? And now, with this notion, we can improve the result of the colored trees. And we can show that if I is a kappa color linear order, we can construct for every F an ordered tree AFI, such that for every F and G, they are equivalent to modulo omega cofinality, if and only if the trees are isomorphic. So now we're just missing the construction, but the construction of the models is given by a theorem of Scheller that is telling us this. So you take T, so we take the trees and then we construct the Ergen-Mostovsky models of the trees. And this theorem is telling us that if the order has these two properties, it's nice and stable, I'm going to define them later, then if the models are isomorphic, then these two SA and SA are equivalent, but in our case, these SA are going to be F and G in our construction. So this theorem is telling us that take a linear order that is nice and stable. If the models that you constructed are isomorphic, then F and G are equivalent modulo omega cofinality. So this is one direction. The other direction is easier because if they are equivalent, we know that the trees are isomorphic, and two isomorphic trees generate isomorphic Ergen-Mostovsky models. Okay, so this theorem will finish the construction. We are only missing to get a kappa colorable linear order that is nice and Weak stable. Is there a kappa colorable linear order so that it's locally kappa nice and kappa stable? So now we have just to construct it. So first we have to define the 11 bits. 11? No. Okay, so the first is we're going to define a representation. So we have a set of sizes mod kappa, set A, and a sequence A alphas. So A alphas is a kappa representation of A if it is an increasing continuous sequence of subsets A, of subsets of A, so that each subset is of size is more than kappa and the union is A. So it's like a filtration. Now we can define what does it mean to be nice, and this is the most tricky notion. So this is a notion of density. So you have like, okay, this is not the actual definition. This is a lemma, but it's the one we're going to use, and it's saying that so you have a linear order of size kappa and a kappa representation. It's saying that if there is a club, so it's that for every delta and x in I, there is a beta with this property. Okay, I will explain the properties. You have the linear order, you take an element in the order, and then you have a delta. So it's saying that there is a beta, so that for every element you take in I delta, there is an element in between these two that is in I beta. But this one doesn't need to be in I delta or in I beta. It could be in general anywhere. But this one is in I delta. That's what it's saying, is that I beta is dense in I delta for these types. And it's getting close. And notice that it's not as strict. It can be one of the two. In case both are in I delta, then we can just see when the first one appears because in delta is a limit. So it's just a density notion. Okay, this is to be nice. And okay. This is just what does it mean the tree to be locally nice, but locally nice just means that the linear order in the successors is nice. That's not a big deal there. Now, weak stable. So a tree is an ordered tree is weak stable if for every small subset of A, B, the types of basic formulas of A over B in A in A is smaller than kappa. So just normal, like the usual definition, I would say. So now we can just ask ourselves, well, so now we can just go through the theorem that there is indeed a weak stable kappa nice, kappa colorable linear order. And now we can finally construct it. So the first thing is we will start by constructing an order that is going to be nice and stable. So let's take the rational, the linear order of the rational numbers. And now we take the product with kappa and we order it lexicographically. So we say that I0 is the set of functions that go from omega into kappa times q, so that fn is equals to f1n and f2n, such that there are only finite many points in which the third coordinate is different than 0. Okay, so that's our set. And the order is the statement that f is smaller than g if and only if fn is smaller than gn in the first part that they are different. So you check where they are different at the beginning, in the first part, and then there is a smaller. So it could be smaller by the first coordinate or the second coordinate. Okay. So obviously I started with this order.
Can if it's below in the second coordinate and then in the first coordinate and then in the other?
No.
I mean, so you take 1 million and then 3 and then 2 million and 0 and 0 and 4, and then you get that one is below the second is below the third, but the first is not below the third.
But
you're mixing the coordinates.
Yeah, you have to have the order of the coordinates. Like it's lexicographical order.
Okay.
So you check for the first one and then the second one. Okay. I think that was what you were asking. Yes. Okay, so obviously I mentioned this one. I took this order because this order is stable and nice. So it's going to be nice because we have there the rational numbers. So if the first coordinate coincide, you can always find the second coordinate someone in between because Q is dense. So you have no problem there. And Q is small, so you don't have problem with the filtration, with the kappa representation. And now, it is stable also because Q is small, and if you only take the first coordinate, that is an example of a weak stable order. So now we just need to color it. And to color it, we just do it by induction. So we start with I0. So these arrows in the top means where do they grow? Where do the order go? So the element in the left is bigger and the element on the top is bigger. The next step, you take every element of I0 and then you take a copy that is smaller but bigger than the rest. So for example, you have here sigma 0, so you take a copy that is sigma 1. So sigma 1 is smaller than sigma 0, but at the same time is bigger than all that is on the left, on the right, sorry, of sigma 0. So just a copy of sigma 0 that is smaller than sigma 0. Now you repeat the same. You have that, for example, sigma 2, it's bigger than sigma 1, but smaller than sigma 0, and so on. You repeat it. So, for example, here you continue constructing. If you see, we are constructing basically a tree that is an ordered tree. So at the end, what we're going to have, and obviously at limits you take the union. So at limit you take you're going to have the union of all. So it's going to be I0, this order of Q, and then in each element we have a tree, an ordered tree that is coming down. Okay. And now the filtration we choose is the one that you can see there. For example, I delta is going to be this small square of length deltas, so that you only go below up to delta in the level of the trees. So for example, if you take two elements, the red ones or the blue ones, you can easily find an element that is in between them, either inside the tree or inside the initial order. So it is nice and we were always just taking copies, so we were not adding new types. So it's also weak stable. So we prove the theorem, we show the existence of that order. So we just take that indeed under these cardinality assumptions, if T is a countable complete classifiable theory and T2 is a countable complete unsuperstable theory, T1 is as much as complex as T2. And the second theorem is that you can indeed prove the isomorphism relation of any unsuperstable theory to be sigma 1 complete. Thank you.
Questions, comments?
The next one.
That was a question. Okay. So that for it, and then what's it? Anarchists? Okay. That was for it, please.
Can you say anything about this assumption you kind of thrown that everybody is really interested in you? You know, haven't pretty much changed.
Which assumption?
I mean, you have there are all these terms. You go back from I guess that's the beginning one, or you have all these functions that kappa is bigger than we continue on. Whereas lambda is bigger than we continue.
Oh, this is because, yeah, you have some iterating where you are making the Ergel-Formostowski model, so you don't want to reach a limit so everything goes. So you see that just to be below lambda, you need a successful. So just that.
So you don't have the little bit part of
Well, you don't have the same argument. I mean, the argument fails because you reach kappa, for example. So you cannot construct a very small model that to iterate.
Question? Comment? Data from line? No, we can thank you again.